classical subpart is A minus BK. B times K. So now right here, I believe. This is 0, 0. Minus 3, 1. Right? Yes.
In your E dot, it should be positive 24 instead of minus 20.
Oh, you're right. Plus 24. Minus 1, minus, a minus 25. Thank you. Plus 24. Right? All right. This is 0. This is really all 2 by 2 of zeros. Right? It's A minus KC. Should be the correct one now, minus 13, minus 1, plus 24, minus 2. Okay, then we have here B, which is, what was B? 0, 2, 0, 2, and this is 2 zeros here. And our C, numbers, is 1, 0, 0, 0. Okay. Fourth order now. And if we look at map here, so nice. The characteristic equation of this whole controller observer we're going to have SI minus this whole big A matrix, which is S minus 1, 0, 0. Well, that is a minus, so it should be plus 1. 0, minus 2 plus 3. 13, 1. 0, 0. S minus 24. Skip one. Oh, I skipped it. This is. Sorry, this is. Sorry, that's 3. And minus 1. Sorry, missed the whole row. So third row, which is 0, 0, S. Minus 13, so plus 13. And it's minus 1, so it's plus 1. Last row, 0, 0. Minus 24. And S plus 2. A lot of zeros here, so it might work out okay. All right. S plus 3, S plus 13, S plus 2, 0, 0, 0, 0. Oh no, 0. This is plus 24? Oh, sorry. Minus 2 1 plus 24 to minus 48. 0, 0, 0. So, fourth order, yeah, funny. You might suspect what some of these roots are, so you can check it. Okay. All right.
Hey, quick, can I just math question? How did you get that 48? What was kind of your process there?
All right, so I'm going this way, which is the first number.
Right?
This ends up to 0, 0, 0, so it's okay. S, 0, 1, minus 2, 1, minus 24. All right? On this one. Correct.
I just
All right,
this process.
we're doing this method. Yeah, right now, I go multiply those, multiply those, multiply those, right? Then you go backwards. S, 0, right? Minus 1, minus 2, 1, 24, 0, and zeros. That's my, I learned that method in high school, and I was stuck with that method. You know, there are other methods you like to do this, but it's, you know, you get your favorite way, or the one you can remember, and you stick with it. That's the one I can remember. Okay? Questions and stuff? Okay, how do I actually put this into a system? The block diagram. Here's our system where we input the U, output Y. It's really all I see when we're doing it. All right, if you look at the observer equations that I've erased here.
Doesn't like how I did it.
Fundamental equation is formal expression for the observer. Because we're trying to estimate this guy. This. Right? What are the inputs to it? So really what I have here is just a x dot, some A matrix, plus, what's this? Two inputs, U and Y. So I take both U and Y. That's the input to this observer. The output is the vector of the states. Okay. Then what do? I'm going to put it in a controller. These are the controller keys. That creates Q. So you're going to build this part, actually build this whole part. These are constants, that's easy. What's this? Oh, I have to make that. What's it doing? That's differential equations here. Right? It's continually running, solving these differential equations. We'll look at how it does that. Let's look at the observer. Right? Here's the integrator. Given x, I have to integrate to get x. How do I create x hat? Well, it's a times ke c. Right? Times x plus e times u plus ke times y. Right? And do those equations. What I'm doing is x dot is equal to this times x plus b times u plus k times y. Well, is equal to that. Right? Right. So what do I actually have to put into the system? Input to the system is what u. This is going to be plant. The output is there. So I need to create all of this. So I need to have some way of summing values, some way of integrating, and so forth. But this is constant. This is a constant. The only trick here is I need to do this integration. So it's continually solving this thing. So it's continually estimating what the states are. It's a dynamic system. Does that make sense, everybody? So when I actually give the system, even though the whole controller observer system is modeled maybe, originally started out second order system, now it's fourth order, what's the order of this part? Second order. This whole part here that I created is the same order as the plant. Same order as the plant. And that's known as a regulator. Yeah.
And in this system, we're just estimating all the states, right?
Yes, we're estimating all the states in this thing. Exactly. We haven't done any minimal state things yet. So I'm reading what's coming from my system. I actually create u, so I don't really need to read it in from the system, because actually creating that, the output that's driving the system. Now, the nice thing about this is MATLAB has software that reduces this whole mess in one nice little step. Right? What I'll do next Tuesday is go through all the MATLAB codes for doing this stuff. Really some very, very powerful stuff. Makes life way easier. So easy, it's like, gosh, we're doing this stuff. I can use MATLAB for it. It's nice to know what it's doing. Now, we put a new computer onto the Quanser system. We do a digital implementation of this. We'll go through after break and how you digitally encode this stuff. You want to put it in break. It's not hard. Okay. Questions on this stuff? Start to make a little bit of sense what we're doing? Controllers, hopefully fairly straightforward. I feedback all the states, make my system behave the way I want. The observers, okay, all I can really read is the output. From the output, I'm estimating what my states are, and it's dependent on what? The letter C is C here. My model, A, B, and C. Right? So from my model, I am estimating what the states are based on what the actual output is in my model, and hopefully tries to correct what that true estimate of these states are. Right? How good it is, how good my model is. Okay, a crummy model, it's not going to work well. Any other question here? Yeah.
Just a quick question, how do you get the X hat that goes down to the control?
Oh, right here. I am doing the sums to create X hat dot, the derivative. Integrate that by an X hat. So this is the dynamic part of it. I'm actually having to do this integration. Right? How do I do that in op-amp? I can actually create this all on op-amp circuits. Did you do that? Good exercise. What's an integrator? Better remember those? All right, give it part of it. What goes in feedback? That's an integrator. Right? So I give it whatever X dot is here. I'll get X, well, there's whatever RC and so forth. I need some gain factor here. Okay? How do we do the sums? Drop down. How do you do sums? Remember that class? Yeah, the electronics. How do I add voltages?
You have like, on the left, you have two resistors parallel.
Well, a bunch of resistors. I need three of them. We got three things we got to do.
Yeah.
All right, whatever the gains are here. Okay. Got one of them. Can we do that? Okay. Another one will be this times a different gain. In fact, I can probably combine these two. Could combine all that together into one. And then the last one is what my output Y is times whatever gain I need